Hi, this is Dr. S.P. Harsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the vibration measurement techniques. So, in last two lectures, we discussed about that what are the basic, the dynamic parameters which we can measure and we can characterize the vibration responses. And in the last lecture, we discussed about that when we are capturing the data, what exactly the data acquisition systems are. And when we are capturing data in the time domain, which sometimes you see are not giving the clear picture about the response features, we need to convert this into the frequency responses. Then you see here we can use the Fourier transformation series in that, and whatever the information is there in the time domain with respect to the this displacement, velocity or acceleration, we can convert this entire information into the Fourier transformation, where we can get the exact exciting frequency with the corresponding amplitude of the vibration masses. In this lecture now, we are going to discuss about again the the vibration measurement technique in the Fourier transformation. That what exactly you see here, we need to put those Fourier transforms when the things are even sometimes in the turbulence manner, or sometimes when the abrupt changes are there in the signal because of some external excitation. Then how do we measure those responses? So, many machines or the processes give rise to the sound or vibration which are not periodic, because you see sometimes even they are either the stochastic, or in sometimes we are saying it is a random, or we can say the transient vibrations. So, when the responses are not the steady state phase or the periodic phase, certainly you see here it is very tough to measure that. So, roughness of the contacting surface between the wheel or path, or for instance we can say that you see here when the gear teeth are meshing and some kind of disorientations are there, or some the different surface roughnesses are there, some irregularities are there on the surfaces of the gear, then certainly you see here we have randomly varying vibration features are there in terms of amplitude and the frequency excitations. Or even we can say when we have the turbulence in flowing media, through which you see here the randomly varying these vibrations are being coming out. So, these random orientation in the vibration, which can be termed as even the non-periodic disturbances, in that the Fourier series decomposition, which we discussed in the last lecture, that you see how we can decompose this information using the Fourier series. So, Fourier series decomposition cannot be made for that. So, what is the solution for these kind of random randomness in the signature? Then we need to use the Fourier transform, means some segmental transforms are there which can be immediately used for that particular time of period, and then we can simply classify, or we can say analyze what exactly the kind of the energy, or we can say exciting frequency or the amplitudes are there in the signal itself. So, if I see that the periodic these pulses, then we can simply find that say at the 0 point we have the amplitude 1 with the period t you see here. So, it is a well periodic feature which can be immediately measured using this the Fourier transformation series or the decomposition, and we can feature it out. But even when we have the pulse width, say with the t this pulse width, and when we are simply multiplying with the alpha, which is something you see this constant feature, then we have even at minus t and t you see we have a clear variation, but with the width of this alpha t. We can say that you see straightway we can find out the coefficient of these complex Fourier series. So, if you are saying that the complex coefficient is delta n for nth type of the signal, then it is nothing but equals to 1 by t, where the time period, the total time period for this is capital T. So, 1 by t. Now, here yesterday we discussed about the entire decomposition, that minus t by 2 to t by 2. Here now, since we are using one of the coefficient here, so we have now the total the total feature in which you see the entire the signal is being considered, it is minus alpha t by 2 to plus alpha t by 2. And in that we can say that since the mean amplitude is 1, so 1 into e to the power minus n omega 0 t into dt. So, then you see we can straightway convert into these two special features. So, we have now e to the power I n omega 0 alpha t by 2 minus e to the power minus I omega I n omega 0 alpha t by 2 divided by I n omega 0 t, or else you see here when we are trying to convert these exponential series into like sinusoidal features, then we have the 2 iota, because you see the cos this cos figure will be cancelled out as we are simply putting this e to the power I n omega 0 this alpha t by 2 is nothing but equals to cos of like this I n this cos of n omega 0 alpha t by 2 plus iota times of you see like sine of n omega 0 alpha t by 2. So, cos will be cancelled out, then we have you see the 2 iota sine of alpha n omega 0 t by 2 divided by I n omega 0 t. So, this is what you see here, the coefficient from the Fourier series which we can compute in terms of you see the sinusoidal feature between alpha t by 2 to minus alpha t by 2. If we are converting this like the total time period in terms of you see the frequency, then we have 2 pi by omega 0 when we are keeping. So, we have now the coefficient delta n is equals to alpha times of sine alpha n pi divided by alpha n pi. So, when we are keeping this into the Fourier series, especially in terms of you see the entire wave formation is in the pulse, then we can say that the Fourier series part f of t is equals to summation for all, right, from minus infinite to infinite alpha into sine of alpha n pi divided by alpha n pi into whatever the exponential features are, means e to the power I n omega 0 t. So, these you see the Fourier series coefficients can be evaluated for various values of alpha, and we can find out that like when we are increasing the alpha or when we are decreasing the alpha, how they are straightway affecting the entire signature. So, you see here now we are taking 3 cases in which the alpha is varying from say half, 1/4 to and 1/8. It is in the decreasing order of that. So, now you see here I am going to show you first the alpha, and we would like to see that how the pulses are being like permitted straightway when they are simply showing from minus like infinite this n equals to minus infinite to this total infinite part, that you see how the things are, how the frequency domains are being like capturing these frequencies. So, the first case which we are going to show that when the alpha is half. So, when the alpha is half, you see now this is a clear picture that like this frequency component n in the x part, and you see here the delta n by alpha, because you can straightway take the delta n over alpha, which is nothing but equals to sine n pi alpha divided by n pi alpha. So, when we are doing this, now we can straightway vary with this delta n by alpha with the n, and you can see that absolutely at 0 we have the first amplitude, that is the period t amplitude, period 1 amplitude, and then the corresponding features are being there with like right from minus like alpha to plus alpha, means up to the 8th part. So, these are the clear excitations which are being there like with this constant amplitude and the frequency component. When we decrease the alpha, means 1/4, now you can see the spectrum. The spectrum is showing the various frequency peaks which is very close to this part, because we know that you see when we just vary the alpha, the discrete spectrum is clearly, you see the dense spectrum rather I should say, is clearly now just like varying with the constant amplitude. So, the first amplitude which is at 0, when you do not have any frequency component, you see we have just period 1 exciting frequency. But as we are increasing the frequency component towards positive or negative side, you see here this is a clear more number of frequency peaks are. And even we can now expect that when we are decreasing now alpha from 1/4 to even further half, that is 1/8, then you can see here this is a clear form of you see like the Fourier series decomposition, when the periodic pulses are there right from this is 0, and then these are you see like if you look at that, they are clearly showing the pulse form in terms of you see delta n by alpha to the frequency component. So, now you see the frequency components are up to 32, the previous case it was for 16 and the previous case it was for 8. So, these are you see the clear variation that you see how many frequency peaks are being allowed when you are decreasing the alpha. So, these diagrams which are clearly showing the Fourier series decomposition for this periodic pulse train with the constant pulse width, that is delta t. So, delta t is absolutely constant in that you see here. So, when we know now you see from that we can conclude that for a smaller value of alpha, say from like 1/8 when we are just coming, there is a clear increasing, and you see like the increasing of period t as we are moving that you see. the frequency component become all more densely packed, and they are absolutely showing that how these like the exciting frequencies are being varied in the band form. But when we have the higher value of alpha, then there is a clear peak of excitation, and you can straightway found that what the tuning part is there when the frequencies the exact the frequency part with the frequency coefficients, or we can say the frequency component n is. So you see here these like alpha 1 half, 1/4 or 1/8, they are clearly showing about that how they are allowing more number of frequency components when we are just going with the decreasing value of alpha. So to derive the relation for non-periodic event when the abrupt changes are there or any kind of impulsive forces are being there in the shock part, we can simply consider a limiting case of period t which becoming like the infinite, and if we substitute the expression for Fourier coefficient as we shown previously, now the Fourier series we can say f of t is nothing but equals to 1 by t summation of, again n, the Fourier this constant is n, which is minus infinite to infinite e to the power I n omega 0 into t. Again here now we need to integrate for minus t by 2, 2 plus t by 2 f of t into e to the power minus I n, the iota basically the iota n omega 0 t into dt. So this is what you see like where we need to keep, because we know that this non-periodic event is absolutely for a very limiting case. So first of all we need to define that where like what is the period in which this non-periodic form of the responses are appearing in that, and then we need to induct those information in this particular Fourier series, where it is a clear variation right from like the coefficient infinite to minus infinite to infinite, and then in between minus t by 2 t by 2 what the informations are there in terms of f of t. So to adopt this limiting case when the period t is just going to the infinite, we know that we need to interchange this omega 0 with what the delta omega is for that particular specific time period dt. Because we know that when we have omega 0 which is 2 pi by t, n omega 0 transforms into the continuous variable omega. So we can say that n omega 0 is now referring to the entire omega. So the important thing here is the step size. The step size in summation become infinitesimally small, because ultimately we need to feature out that what exactly, because here if we are taking like this our step size is bigger, then we cannot feature it out exactly that what kind of variations are coming under non-periodic form. So we need to just capture like at the very small, means infinitesimally small like size, the step size, and then here we can simply sum up entire feature in like in the transformer equation towards the integral form. So now here with this concept, now when we are going to the Fourier series f of t is nothing but equals to 1 by 2 pi. Now it is being converted into 1 by 2 pi, as we discussed already that this omega 0 is now being converted into 2 pi by t, and then when we are just going with this, we know that f of t is 1 by t. So now we have 1 by 2 pi into minus infinite to infinite e to the power iota n omega 0 t into now whatever the information which we are saying that like the Fourier transform of the signal. So we need to go that what exactly the signal information which is showing the non-periodicity like, and what the informations are there towards that. So we have into minus infinite to infinite f of t e to the power minus iota n omega 0 t into dt, and then it is dw, because ultimately we need to convert this entire omega 0 which is being there into dw as we discussed. So certainly here now, and n omega 0 is referring to the omega part. So we can straightway put here into d omega, and the expression inside this part means f of t into this e to the power minus iota n omega 0 t into dt can now be identified as the Fourier transformation of the signal, and we can say f of now omega is nothing but equals to minus infinite to infinite f of t e to the power minus iota omega t into dt. So now when we are doing the inverse transformation, this Fourier transformation, then we have f of t, because of this the Fourier transform f of w is there. So when we are doing this inverse transformation, we have f of t equals to 1 by 2 pi minus infinite to infinite f of omega e to the power iota omega t into d omega. So, this is what you see here, the inverse Fourier transformation, which contains the like the non-periodic form of the signal information. So, the Fourier transformation is certainly a complex quantity, like which in case f of t representing the force, and with this you see we have the Newton per unit hertz. And in order to like a finding for f of t, which is to be very real, we can say that f of minus omega is nothing but equals to f of omega, this f of omega, and you see here when they both are equal, we can say that we can find out f of t for the real terms. Now, we are taking the example in which you see here we have the Fourier, we need to calculate the Fourier transform for a single force pulse, and the pulse width is given as Tp, which you can see that it is varying from minus Tp by 2 to Tp by 2, and this is what you see like the direction f of t with the t. And when we just want to find out, you see we need to have the Fourier transform for this. So, f of w is nothing but equals to minus Tp by 2 to Tp by 2 integration f, which is being applied here, you can see this f bar. So, f bar into e to the power minus I omega t dt. So, you see here we can straightway calculate that what is the variation of this force with respect to, you see here like the Fourier transformation, we can say the pulse form of force. And now, when we are keeping this, so f of w is nothing but equals to f of f divided by I omega into e to the power I omega Tp by 2 minus e to the power minus I omega Tp by 2. So, when we are trying to calculate this f of w, which is nothing but equals to f into Tp, now we know that when we are just trying to formulate in terms of sine and cos omega, you see here means omega Tp by 2. So, we have sine omega Tp by 2 divided by omega Tp by 2. This is clearly giving us not only the amplitude, but also you see here the phase. So, our interest is right now to see the amplitude of the spectrum. So, amplitude of the spectrum becomes now the modulus form of this f of w. So, f of w modulus is nothing but equals to f, that is you see like the whatever the force in the single pulse magnitude f into Tp modulus of sine omega Tp by 2 divided by omega Tp by 2. So, this is you see in the Fourier series my like the amplitude is there in the single pulse. So, Fourier transform is real, which implies that the phase spectrum is determined by the sine of this sine alpha Tp by 2. So, Fourier transformations amplitude spectrum and the phase spectrum, these two are simply like we are going to discuss about that, which simply says that when you have the dimensionless frequency with respect to you see like delta Tp, which is being incorporated in that, we need to transfer the rectangular form of pulse into like the real form with the delta the alpha tends to 0. So, the discrete spectrum for this pulse train, now in this case particular single pulse, is transformed into the continuous like the spectrum form. So, when we are doing these things, now you can see that we have a clear this magnitude form Fw by this modulus of Fw divided by Ftp, and you see here at the 0 we have the maximum amplitude, and then you see here these like the wave transformations are there, as we are, because we know that we can characterize with the using of the like this sine part, especially with the sine of alpha into like Tp. So, when we are just trying to move with this omega Tp, then we have you see here whatever the changes are there with the 2 pi, 4 pi, 6 pi and 8 pi, you can see that we have a clear this like the amplitude is 0, but in between whatever the variations are there, though you see the amplitude is clearly varying as we are moving towards even the 0 to 8 pi or 0 to minus 8 pi, and these you see the amplitude is decreasing. Or when we are going with the, now this is what you see my amplitude, and when we are going with the phase part, the phase is nothing but equals to like when we are just trying to capture like for this Fourier transformation the phasor spectrum. So, the phasor spectrum is clearly showing you see that when we are just going from you see 0 to pi part, 0 to pi, then you see this is you see at for every entire part, means when we are just going from 0 to minus 8 pi or 0 to 8 pi, the variation is very clear. Exactly at this 2 pi you can see that the maximum phase differences are there, then they are being constant. Then again you see the phase difference from pi to 0 when we are just approaching to at the 4 pi, at the 6 pi and at the 8 pi. So, similarly you see here at the minus 2 pi, minus 4 pi, minus 6 pi and minus 8 pi, there is a clear phase shifting is there for this kind of Fourier transformation. So, like when we are trying to simulate these two features, then we will find that the amplitude this particular part, the amplitude spectrum is clearly showing that when we are trying to move from 0 to 2 pi, means this omega Tp at the 0, at 2 pi, at 4 pi and 6.8 pi, they are showing 0, but at the time there is a clear phase shifting is there in the phasor part. So, we can say that by the analysis of the transient forces in the time and the frequency domain, we can say the number of general conclusions can be made, and you see here through that we can clearly feature the response analysis, that you see here what exactly the response is saying in terms of the amplitude and in terms of the phasor, and that is very we can say helpful information for designing part. So, the smaller of the impulse means when we are going for the small amplitude of the impulse part, and the lower amplitude can be clearly featured out within the frequency domain. And you see we just want to see the effect of the two different modification in the pulse, and what the modifications are there now we are going to use, and here we are using you see the dimensionless frequency f into Tp part there. So, now you see if you look at that, we are basically focusing here that when we are trying to change, means when we are trying to modify the impulse, then what exactly there. So, you look at that, we have you seen the sound part here, and you see this is what my frequency, then a dimensionless frequency f into Tp. So, as we are just moving from you see with this is what my Tp feature, this Tp and I equals to Ip, that is what my impulse feature. So, when the impulse and you see the T, these it has the clear relation is just like that, we can simply see that when FTP, the non-dimensional frequency, is 1, now this amplitude, whatever this amplitude is there, it is just coming 0, and then you see here it just remain you see for constant some time -10 I should say, and then you see again the pulse is being there, which can be again formed in this way because of my this time period Tp. Now you see here it becomes going like that. In the second case, when you can see that when we are just going with the Tp by 2 to Ip by 2. So, now you see we simply bifurcate this entire signal into say the positive side, where the half of Tp by 2 and you see the Ip by 2 is the intensity part is there of the impulse. Then we can see that at FTP, you see this there is a clear amplitude of this you see the signal is absolutely going up to the maximum, the 2, when the total completion is there. And when we are going with this I equals to Ip by 2, means we are simply just lowering the amplitude of the impulse say I, which is nothing but equals to integration of Ft into dt. So, this you see here when we are just trying to go with this integration of Ft into dt with the half Ip by half, and but we are not changing the time period, just like in the previous case we converted both into the half, but here we are keeping this one. We can see that this amplitude is just coming down, and you see here it will be at the lower phase for maximum time, and then the another you see the peak will be formed in this way. So, when we increase the duration, or we can say rather the pulse width Tp in the time domain, which simply translates into the lowering of cutoff frequency, and generally we are just taking the frequency at which you see the level has fallen 3 decibel point with respect to the maximum amplitude. That is what we are saying, that the cutoff frequency. So, the 3 dB sound the sound level this is one of the standard feature at which you see whatever you see the maximum amplitudes are being there, we can say that this is my cutoff frequency. So, by making the pulse with the longer you see duration, means when we are increasing the duration, the lower frequency excitation can be immediately obtained. And this can be and that is why you see here when we are just going with the half of Tp, you see that we cannot get that what exactly the lowered form of the exciting frequency, the total you see the blurred features are there, and it is just bypassing the entire FTP part. So, that can be exploited to shift the excitation into the frequency band which is less disturbing, or we can say in which the structure is not as effectively excited at the lower frequencies. So, you see rather we can simply show that when the T is infinite, when the T is infinite, you certainly you see here in these Fourier series there is nothing you see here, it is absolutely the 0. But when we are now going with this t equals to t0, that means you see here this time step is very short. Now you can see this information is absolutely like coming down, and then this is clear. This is clearly showing that at what frequency feature we have excitations. And then you see now we are increasing this time period, you see say in the feasible manner 4 times of t0, you can see that all the number of frequency excitations are clearly exhibiting in the frequency spectra with the variation of their amplitudes. And when you see here we are just taking that, you see when we have the Tp, and in this Tp particular you see when we are just trying to see that what exactly the variations are there below, you see this is what you see like we can say 2, now we are changing only up to 1.5, you can see that it is clearly showing the variation with the time response Tp. So this is the beauty of the time like amplitude, means when we are just going with the like more the increased form of the pulse width, certainly you see here we need to check it out that how the information is to be translated into the lower form of this cutoff frequencies. So if the rise or fall time of the pulse is lengthened, means if we are just going towards more length of that, the amplitude decays more rapidly with the frequency, and you see here we can say that at above cutoff frequency there is a clear we can say decays are there of the cutoff frequencies. So this can be exploited to reduce the high frequency content in the excitations, and also we can apply to higher time derivatives for that. So we need to check it out that how like the rise or fall is there with the pulse, and we know that since the amplitude is clearly decaying at a faster rate when we are just like talking above you see the cutoff frequencies, then we need to check it out that like the high time derivatives, how we can apply these things to that. So the more rounded, or we can say the soft excitation in the time domain, more rapidly the high frequency content decays are there. So if we do not have you see like a clear peak of excitations, when we have the rounded form is there, then certainly we can simply like justify that it is like the fallen feature in these amplitude is more rapid like in terms of you see the high like frequency contents. So now we are going to the another example. In this you see here the nature of periodic force applications like just we can simply apply this force application that bring about the sound and vibration determination, how great the problems that arises are. So now you see we are simply showing the Fourier series decomposition of the rectangular wave, a triangular wave, and the sine wave. So you can see that this is you see the first is like the square wave is there, and this is what the feature of the square wave. And now we can see that what the variation of the amplitude is there with respect to the frequency component n. So this variation is clearly you see like at all these component up to say like the 19 component, these are the variation in the amplitude when the frequency this waveform of these like propagation is the square wave. And when we have the triangular wave feature is like that, you can see that even for all the 19 exponent what the variations are there when the decay is there of the amplitude. This is also decay, this is also decay, and the third form when we are just taking you see here the sine wave, then this is you see here the frequency component 90, and you see this variation is there. So the amplitude of these overtuned decay more slowly for rectangular wave, as we can see that like 1 by n is there for the decaying part, where the n is nothing but the nth frequency component. Then for the triangular wave where the decay is 1 by n square. So this is the pretty clear picture is there that when we are just looking to the rectangular or you see the square wave, and when we are talking about the triangular wave, the decay is you see this is what the drastic decays are there, because the dependent feature is 1 by n square, where you see the decay is very slow because the dependent feature here in this square or triangular wave is 1 by n. And because the overtune like often fall in more disturbing distributing this frequency band, we can say it is a good design principle which always make force like application as a soft or even more towards the sinusoidal feature of the decaying part in the like all these variations with the time domain. So when we are going towards that, you can see that when the sine wave curves are there, they are the softened part and they are simply showing a streamlined motion along the path. So we can say that you see when we have the sinusoidal feature, this is a clear peak of excitation, a clear tone is there exactly at these particular, like the dedicated frequency component, and the variations are like that. So another phenomena that occurs in the case of periodic forcing is the distance is delta f between the frequency component, and when it becomes larger, the shorter period t can be clearly showing that you see what exactly the exciting peaks are. So we can say that for a periodically like the repeated rectangular pulse, we can simply feature out that like when we have this square, when we have the triangular, and when we have this sinusoidal wave, what kind of you see the excitation peaks are being there. So the fact that you see we can use to minimize the number of frequency component excited in the sensitive frequency band, only we need to check it out, you see what exactly the peak forms are there. So now you see right now we have this Tp is nothing but equals to 0.8 like the millisecond, and you see here we just want to find out, you see for this t by 5 that is nothing but equals to 0.01 s. So now you can see that at the frequency whatever like the exciting frequency, we have a clear tone, and you see here the sensitivity of these frequency like this sound with the frequency components can be clearly showing with the kind of exciting frequency component n. So you see here that can be straightway show that what the exciting frequencies are there and how we can get that part. So this was you see the example in which you see it was clearly showing that when you have a different frequency component, like you see when you have a rectangular or the square wave or the triangular wave and the sine wave, then how the features are being there in terms of you see like the amplitude and the corresponding exciting frequency. So this is you see all the diagram they are clearly showing. Now in the next example we are taking the sound pressure level, which is being carried out you see like always at the third octave band with center frequency 800 hertz, 1000 hertz and 1250 hertz. So whenever we are trying to see that you see when the octave bands are there, what is my central frequency, and then what is corresponding you see the sound power is, means in terms of dB. So when we are saying that when we have the central frequency say 800, so the sound power in this, the sound pressure level is you see the 73.4 decibel. When we have the central frequency 1000 hertz, and if we have 69.8 dB, 1250 is 1250 hertz is my central frequency, correspondingly 72.1 is my sound pressure level dB. Now we just want to calculate the sound pressure level for octave band with the central frequency you see if we have the 1000 hertz. So certainly you see here we need to just go first that what the mean squared value of my sound pressure in the third octave band, and then you see here we can sum up the mean squared values in accordance with the like this Parseval relations. So we know that the Parseval relation says that this p square like this octave band is nothing but equals to p1 square if we have you see the three values. So that means the three sources are there. So p1 square plus p2 square plus p3 square. So first of all we need to find out you see what the square terms are there with this. So we have you see the frequency at 8000 and 1250, the p square is clearly showing that it is like the 8.75 into 10 to the power 3, 3.82 into 10 to the power minus 3 and 6.48 into 10 to the power minus 3. So you see now we can simply calculate the sound pressure level LP, which is nothing but equals to 10 into log of p octave square divided by p reference square. And when we are like calculating the p octave, that is nothing but equals to p1 square plus p2 square plus p3 square. So this we can simply find out the 1.91 into 10 to the power minus 2. And when we are keeping this now with the p reference, that was you see 4 into 10 to the power minus 10. So now we have the 10 log 1.91 into 10 to the power minus 2, which was being calculated as p octave square, and p reference square is 4 into 10 to the power minus 10. So we can get you see the sound pressure level 76.8 dB. So we can calculate the like this part especially when you have you see all the frequency levels together there itself. Now in the last example we would like to see that when we are just like exciting the machine and how we can design the foundation especially with terms of you see like the isolator. So machine with its like foundation is like just exciting at the periodic force, and we can approximate this by the sine by the square wave, as I am going to show you that. And foundation vibration at 250 hertz becomes the problematic. So now this is my threshold limit that I need to go up to 250 hertz, that when I am going up to 250 hertz, then the problematic features are being there due to structural resonance at the frequency close to that 250 hertz. By incorporating the vibration isolator, the force excitation can be modified to some of the approximation a sawtooth waveform. So now we are changing the waveform from the square to the sawtooth waveform. So you can see that this is what you see here, the two main forms are there. The one waveform is this, you see here, where we have the squared feature, and this is what my like the time, and this is the amplitude variation of the forces are. And when it is being sawtooth feature, then again you see here, this is my another feature of when we are simply adopting the vibration isolator. Now we need to calculate the Fourier series for these signals, and also we need to calculate the amplitude of the force spectrum of the two signals at 250 hertz. So first, the Fourier series expansion for the square wave. So when we have the square wave, we know that the f of t is equals to like a 0.1 t in between minus t by 4 to plus t by 4. As you can see that this is what it is. When I am saying that my t is this, so minus t by 4 to plus t by 4, you see here in this entire, in like we can say the spectrum, we can get, you see, the pure form of, you see, that the total information of this Fourier series component. So if I am just talking about minus t by 4 to like t by 4, I have f of t 0.1, and when I am going below means minus t by 2 to minus t by 4, then it is minus 0.1, and when I am just crossing this means t by 4 to t by 2, then you see here I have minus 0.1. So this is what the variation is there in the square wave form when I am just like crossing the right from 0 to minus t by 4 and plus t by 2 plus t by 4, it is just 0.1, and then before that below and after we have minus 0.1 as f of t, because you see we have the t as 0.02 second. Now we need to take the any instance and we need to calculate the complex Fourier series. So we are saying that we need to just go with the coefficient delta n, as discussed already. It is nothing but equals to 1 by t integration of minus t by 2 to say minus t by 4, the first one. I know that my f of t is minus 0.1, so I can keep, you see here, minus 0.1 into e to the power minus iota n omega 0 t into dt. The second 1 by t, now it is from minus t by 4 to plus t by 4, and you see here it is the positive f of t. So we have 0.1 into e to the power minus I omega 0 and t into dt. Plus now you see here, now we are going towards further part right from the t by 2 to t by 4 to t by 2. Then it is, you see, again f of t is minus 1, so minus 1 e to the power minus iota n omega 0 t into dt. So when we are now summing up all these things, now we have delta n, which is coefficient is 0.2 divided by n pi sine of n pi by 2. So these, you see, the variation of this particular, we can say the complex form when we are considering the square waveform. Now if we are going with the triangular waveform, then certainly I have the f of t, the Fourier transformation is 0.1 plus 0.4 t by t when we are just going with minus t by 2 to 0, and when we are going from 0 to t by 2, now this is what my width for the triangular waves are, then it is 0.1 minus 0.4 into t by t. So with this t 0.02 second, now we can calculate, you see, both the things in my coefficient, the complex coefficient. So delta n is nothing but equals to 1 by t integration of minus t by 2 to 0, 0.1 plus 0.4 t by t into e to the power minus iota omega n omega 0 n t dt plus 1 by t, now 0 to t by 2. So now it is 0.1 minus 0.4 t by t into, you see, we can say that e to the power minus iota n omega 0 t into dt. So when we are trying to do these things, now we have, you see, the two main features. When the n is, like the odd number, then we have 0.4 divided by n pi square, and when the n is of even number 2, 4, 6, then the delta n is equals to 0. So this is what you see, the first part in which we can simply calculate the Fourier coefficients, the Fourier series particular for both the signals when we have the squared part and when we have the triangular part. Now the second is we need to calculate the amplitude of the force of like the force spectrum for both the signals. So now we are going to this, the amplitude of the force spectrum at 250 hertz. So first of all we need to go that what is the exciting frequency for this. So omega 0, which is being there, you see, like a 2 pi by t, or the t is given as 0.02 second, we have the exciting frequency 50 hertz. So we know that when you have the natural frequency 50 hertz, so certainly at 250 hertz the coefficient, this Fourier coefficient is n equals to 5. And when it is there, you see, now we can keep and we can get for a square wave the delta n is nothing but equals to 0.2 divided by n pi, and delta 5 is nothing but equals to, when we are keeping, you see, n, then it is 0.04 by pi. And for triangular wave, which is nothing but delta n modulus is nothing but equals to 0.4 divided by n pi square, we can say delta 5 is 0.016 by pi square. So this is all about, you see, like the this particular chapter, in which, you see, we simply analyzed the information whenever we are capturing through our through our sensors in terms of the time domain, and you see the information is not periodic one, which is one of the specific, you see, like we can say application for that. When the machine is running all the time, we cannot get, you see, like the periodic form, the turbulence or the non-periodicity is there, then we need to take the Fourier transform, we just pick that part, we need to feature it out with the using of, like this coefficient alpha, when we need to go with the lower value of alpha, so that we can like incorporate the broader band of the frequency, and then we can just take the this infinitesimal step at that point wherever you see these abrupt changes are coming, and we can simply get the Fourier transforms for that particular value in terms of, you see, whether our sine wave, our square wave, triangular waves are there of the wave feature. Now in my last lecture I am going to discuss about the filters, that how we can select the filters, what exactly the basic like these featuring the parts are there in the filters, and then you see some of the numerical problems like again for like the vibration measurement and the control part. Thank you.